In this video, we'll talk about the definition of potential energy for different systems. And then from there, we'll talk about energy conservation. Okay? Alright, so what's potential energy? The definition is the following. It's defined as this energy. Okay? So let's call this U. U is the symbol for potential energy. Is a function of position. Let's use this R vector to represent. So it's a function, basically it's a function of position. And potential energy is defined for a force. So it corresponds to a force. It will be related to the work done by such a force. Related to work done by a force. Okay, so I said force a lot of times now. Does that mean every force can be used to define a potential energy? The answer is no. Right? The force need to satisfy a certain condition in order to have a definition of energy, potential energy. So what kind of force can be used to define potential energy? And we talked about this in the previous chapter when we define work. We talk about work done by conservative forces. So only conservative forces can have the definition of potential energy. Now here are some examples of conservative forces. Gravity on the Earth's surface. And gravity in general. Let's say we're not limited to the Earth. We can go beyond the Earth's surface. We can also define that conservative force, potential energy for that conservative force. And we have spring forces. For spring force, you can also define a potential energy. And also electric force. Electric force is also a conservative force. You can define potential energy for such a force, etc. Okay, now we're going to start talking about like different definition, different forces, their corresponding potential energy definition. Okay, but we need to have like a general formula for define that, right? So the conservative force is work. Let's call it let's say W. Let's call it work. Let's call it WC. C represent work done by conservative force. Okay, it's called WC. And it turns out that the work done by conservative forces in a certain process equals negative change of the potential energy. Okay, so let's write out this delta U. Delta U is U final minus U initial. Okay, sometimes I use U naught, sometimes I use UI. They're interchangeable. They're the same. They represent some initial state, initial energy, etc. Okay, so that can be said as the definition of potential energy. Okay, this equation. Alright, so let's look at several specific forces, and let's look at the definition for such forces. Let's first think about the gravity on the Earth's surface. Now, in order to define, remember the potential energy is a function of the position, right? So we need a coordinate system so that we can specify the position's vector value. Okay, so let me draw these coordinate system. Let's call these y-axis, and for the vertical direction, and the horizontal direction we call it x-axis. Okay, here's the origin, and the origin level is, let's call these, we'll see later on, is 0 potential energy level. We'll see this in a few seconds. But now think about the work done by such a force if I move an object from its initial yi, xi, this position to a final position here. Now we have y final, x final. And this movement can be along any path. Let me draw one of them. Remember, that's our definition of conservative work, conservative force. So let's look at one intermediate position. Here, the gravity is acting on the object. Let's call this Fg. And we can also draw a tangent line for this path, and let's call it ds, infinitesimal displacement. Okay, now the definition of the work would be, in this process, the work done by gravity is Fg dot ds. Okay. So we did this before in the definition of the work in a work calculation, and we can just repeat this quickly. Okay, so Fg in terms of the coordinate system x and y's unit vectors is given by negative mg j hat. Right, because it's along the negative y direction, so it's negative j. Mg is the magnitude. Dot ds. Now ds, let me write it here. Ds can be decomposed. Let me move this ds to a new location, and we can see it. Okay, so ds equals, the decomposition is dxi hat plus dy j hat. Okay, so we have that decomposition. Then let's write this down. Now we need to distribute the j hat here into these parentheses, and so we do j hat dot I hat, which will be 0, j hat dot j hat, which will be 1. Okay, so we can get negative mg dy. Okay, in the end, you get negative mg dy, and the integral here goes from initial to the final position. Initial to final position. Now here, since we only have dy left, so it means that the work done by gravity only depends on the y-axis. So that's why I only need to write down yi, y final. Now this integral gives us negative mg y final minus y initial. Okay, that's wg. Now let's recall the potential energy definition. The work done by conservative force equals negative delta U. So let me rewrite this as negative delta U. Okay, that's our definition for the potential energy for an object on the Earth's surface. And delta U meaning is U final minus U initial equals that, right? So that's why we can associate U final with mg times y final. Okay, so this product here, and ui with yi product with mg. Okay, so let me write out this association. U final equals mg y final. U initial equals mg y initial. Okay, now when we talk about this integral, we pick these x, y, initial and final positions arbitrarily, right? We didn't specify any special property of these 2 points. So that means that we should have U, the potential energy definition, as a function of y, which is mgy, and that will be for any y. It's not limited to initial and final. It actually applies to any y positions. Okay, so that's why this equation is the definition of the gravitational potential energy on the Earth's surface. Okay, so let's write out this. Uy equals mgy. Okay, now I need to point out one thing that is important: the coordinate system direction. Okay, so the y coordinate need to be upward. So the definition is based on the coordinate system where y-axis is upward. Okay, now if you define y-axis downward, then the definition of U will change. Will change, I think, by a sign. So that's why you need to be careful about the coordinate system. You need to be upward. Okay, need to be upward. And also, I point out at the beginning that this origin here has a special meaning. It means that the potential energy at this energy level, at this level, horizontal level, is 0, right? Because all the points along this line, this horizontal line or horizontal surface, has y equals 0. Okay, all the points has y equals 0. So that's why the origin. Another thing I want to say about this definition is the origin level means the whole plane that contains the origin has 0 potential energy. Okay. All right. So now think about the spring system. Spring potential energy. Now here is the spring system at various situations. Okay, so now let's say here is the original length of a spring, and we attach a mass m to the spring that has spring constant k, and right now is the original length of the spring. So we want to use this point as the origin to build a coordinate system. It's this origin O, and then the x-axis is this way. So the concept here is the same as before. The origin always gives us the 0 potential energy level. Okay, so it's similar here for the spring system. All right, so now imagine that we pull the spring to a position x. Let's call this xi with some initial position xi. Okay, and then later on the spring moves to even longer this position. Call this x final. Then we want to talk about the work done by the spring in such a process. Okay, so first the spring force is, its magnitude is k times x. Okay, so if you pick let's say there's an intermediate process in the middle between xi and x final, there's a x position. Okay, then we have the magnitude here given by kx, and x, if you compare to the origin, which is the original length of the spring, there's an additional length x, right, related to the spring stretch. And that's Hooke's law. This equation is Hooke's law. Now we want to make this equation a vector equation, because later on we're going to calculate the work done by such a force, so we need a vector there. Okay, so that's why I want to rewrite this F spring as a vector, and then put I hat here to represent the unit vector along the x-axis. But the spring force, let's draw the force diagram. So the force is this way, F spring is this way, right? It's pulling the object back toward the origin. So we should add a negative sign here because it's opposite to the x-axis direction. Okay, so let's see the work done by the spring in such a process is F spring dot ds, okay, from initial to the final position. And let's write out the F spring negative kx I hat. Okay, so that's the expression for F spring. Now ds, think about ds here. Okay, so ds is an object's displacement along the path, and in our case here is a one-dimensional system, so it's simply just dx I hat, simply just one component, unlike the gravitational force case where we have y component, right? So here we don't. So it's dx I hat. Now it's much easier than before. We just have I hat dot I hat, which is 1. Okay, so we have from initial position xi to final position x final negative kx dx, and that integral can be done easily. We have negative 1/2 k dx squared, right? So we can pair it up, and then x goes from x initial to x final. So let me write out here negative 1/2 k x final squared plus 1/2 k x initial squared. Okay, but that equals, remember, negative delta U when I define the potential energy for the spring system, and that equals negative U final minus U initial. Okay, I want to do something here. I want to rewrite this term as negative, pull out a negative factor, and inside the inside the parenthesis we have Yeah. Now inside parentheses we have negative. Inside parentheses we have 1/2 kx final squared minus 1/2 kx initial squared. Okay. Now the reason we change the negative sign here is because there's a negative sign outside. So that will, when we combine these two negative signs, we get positive. Okay, we go back to the original equation. All right, so now I can associate these u final with this term and ui with this term. So we have u final equals 1/2 x k x final squared. U initial equals 1/2 k x initial squared. In that case, in that sense, we say u is a function of position x equals 1/2 kx squared for any x position. Okay, because the reason is just like before, initial and final, they are arbitrary. They're arbitrary. We didn't pick any special positions, so that they will represent any position, any arbitrary position x. Okay, so that's why let's write out here. So the potential energy for a spring system is ux equals 1/2 kx squared. Okay. Now we need to be careful. This x here is the additional length to the spring original length. It's something extra, so there's an extra length, extra stretch, or on the left side is the extra compression. So let's say there's an object here, the object is here, and there's a compression of x. Then we also have that potential energy for springs compression. Okay. Now the zero u level is the origin, right? Is the original length of the spring. Okay, so that's the spring's potential energy definition, and we can actually go on to talk about, let's say, the potential energy by the general gravity and also electric force. But I'm going to reserve these for the future because we have a specific chapter talking about the solar system. There we're going to talk about this general potential energy definition. Okay, also in the electricity, magnetism, we're going to talk about this electric force, potential energy. So that's why let's skip them right now. And let's define, since now we know two energies, kinetic energy, and potential energy. Then we can define this so-called mechanical energy. The symbol for mechanical energy is E. Okay. Now, the kinetic energy we use K there, right? And potential energy we use the U there. So this mechanical energy is defined as K plus U. Okay. It's defined as the called the total energy of the system. And let's write out for different systems. Let's say I'm looking at an object on the Earth's surface. Then I'm going to write down this 1/2 mv squared from the kinetic energy plus mgy. Y is the y coordinate of the object. Okay. Now for the spring system, E equals 1/2 mv squared plus 1/2 k x squared. Okay, so that's the potential energy for the spring system, and it's called the mechanical energy. And you probably also know there's a theorem called the mechanical energy conservation. It says that in a certain process, the mechanical energy that we defined in the above, let's say E here, is a constant. Okay, it doesn't change in some process. And the reason we can have this energy conservation is because the reason we have is because work done on the system, is by conservative forces. Okay, so we can have gravity doing work on a system and only gravity. Then we have this mechanical conservation. And if for a system we only have spring force doing work on it, then we have the mechanical energy conservation. Okay, and why is that? Let's think about the potential energy definition. So we said that the work done by conservative force, right, equals negative delta U. Now, if we have this condition, right, the only work done is by conservative force. So that means that the total work or the net work is the work done by conservative forces, right? In general, we have net work equals work done by conservative force and work done by non-conservative force. Okay, so that's work by non-conservative forces. Okay, and some examples are, let's say, friction force Fk, tension force T, and pulling force Fp, etc. All those kind of non-conservative forces. And work by conservative forces. Some examples are gravity mg, F spring, etc. Okay, and that's why we need to have this condition, because only this condition is true, then we have energy conservation, right? So that's why the net work, the total work, is only by WC, and there's no work done by non-conservative force. Okay, so that's why usually if you want to apply mechanical energy conservation, you need to check this condition. Check if this one is true. Okay, and all right, so now we have total work or net work done by only conservative forces. So we can go back here, because net work equals delta K, right? That's the work energy kinetic energy theorem. Sorry. Then we have that, right? So this one equals delta K. Okay, now what's delta K? Delta K is K final minus K initial. And what's delta U? Delta U is U final minus U initial. Okay, now if I rearrange all these terms, such as I move U final to the left side, K initial to the right side, then we get K final plus U final equals K initial plus U initial. Okay, so you see the importance of this potential energy definition, it actually guarantees this equation, right? So we need to define this potential energy properly so that we can have this quantity that is constant or that is conserved. Okay, so that's why we have this E equals constant. Okay, so now we understand the mechanical energy conservation, and in order to apply it, as I said, you need to check there's no work done by non-conservative forces. Then you can safely apply this equation to solve some problem. But there's also this general energy conservation. And it says that if there's work done by non-conservative force, okay, so this term is not zero, then there's energy conversion. So the mechanical energy will be converted. Actually, I need to, yeah. So will be converted into like other forms of energy, either going this way or that way. Other form of energy will supply energy to increase the mechanical energy. Okay, so let's look at some the general formalism, and then we'll talk about some examples conceptually. Remember, we have W net, right, equals work by conservative force and also by non-conservative force, and W net according to the according to the work and kinetic energy theorem equals delta K, right? And WC here, the conservative force, the work done by conservative force, still equals negative delta U. Okay, so that plus WNC. We just have this additional term here, and that's why it's called a general energy conservation. Okay, so let's see. We have, if I expand this term, K final minus K initial equals negative U final minus U initial plus WNC. Then we can see K final plus U final equals K initial plus U initial plus WNC. Or you can say E final minus E initial equals WNC. Okay, so that's the another important equation. Sometimes we can apply it to do some calculations, such as what is the work done by non-conservative force. So we can look at the mechanical energy change that give us exactly the work done by non-conservative forces. Okay, so this equation is called the general energy conservation, because we do see some energy conversion here. So in this case, we can relate the mechanical energy change to this other form of energy through the work done by non-conservative forces. Okay, so let's look at one example. Let's say there's a block sliding on the surface, and it has initial velocity V initial and final velocity V final. And there are three forces acting on this object. So normal force, gravity, and Fk. Okay. Now the work done by normal force is 0. The work done by gravity in this case is also 0. So that means that there's no potential energy change, right? So because of this, there's no U change. U is a constant. But we do have work done by Fk. Okay, so let's see. Fk, let's say there's a displacement delta x. So the work done by Fk is Fk dot delta x equals negative Fk delta x. So the result here is negative. The work done by the friction force is negative. Now, according to our general energy conservation formula here, then we will say E final minus E initial equals W Fk, which is negative, right? It's negative. So if I write out these E final, E initial components, so K final, U final minus K initial, U initial, then we have this term negative, right? The summation here negative. And because U doesn't change, right? We're looking at the same level. So what we have here is actually just the loss of kinetic energy. There's a kinetic energy loss in this process, okay? And the mechanical energy also has a loss, right? So that's a loss of E here, right? Delta E is negative. So where do those energies go? Where does those energy go? And the energy is from goes to the surface. Okay, so you can look at the surface here. Surface is heated up. So there's a surface between the block and the horizontal surface. The surface is heated up, okay? And that's what we call thermal energy. Whenever temperature changes, then there's a change of the thermal energy, okay? So in this case, is mechanical energy turns into thermal energy. Okay, so that's the energy conservation. Now, lastly, I want to talk about quickly the force and potential energy. Relation. So now we know potential energy here, U, is in general a function of x, y, and z, right? It's a function of that. Then we can say, how about this? I expand this U along some point, and I can do that expansion just like in the Taylor series in mathematics. So I have partial U. If I take a derivative of U with respect to x, and then I multiply dx, okay? And also for the right side here, for the other term, other directions here, I have partial U, partial y, and then dy plus partial U, partial z, and then dz. Okay, so it's like we expand this quantity and along a point, and then we call that delta U, right? So delta U is like the expansion. Let's call some position U naught, and then going away from it, we have delta U. Okay, now this delta U can be expanded in this term. Now, on the other hand, we know delta U is negative W, right? The work done by conservative force F. And such a work is F dot ds right? But I don't want to use this integral sign here because I want to relate it to the delta U, which is in this form, right? So let's see, we have negative fx dx. Okay, so if you think about this dot product here, okay, we have this expansion fy dot dy and then fz dot dz times dz. In fact, I should change something here. I don't want to say this integral, okay? Instead, I want to say there's an infinitesimal amount of work dw. Then dw is given by negative f ds. Okay, that way it's easier to relate to delta u. Now let's put this to delta u equal to delta u. Okay, then compare each term by term. The first term, fx, is related to negative partial u partial x. Second term, fy, is negative partial u partial y. Third term, fz here is negative partial u partial z. Okay, so that's the force and potential energy relation. If I know, like for an unknown system, if I know it's u, x, y, z expression, if I know this one, then I can calculate each component of the force. Okay, so let's do some examples here, which we already know. So now let's say I know u is a function of y, which is mgy, right, for a certain unknown force potential energy. Now, according to our equations here, I can say its fx is negative partial u partial x, which turns out to be 0 because there's no x dependence. Now fy is negative partial u partial y equals negative mg, right, equals that. Fz and fz equals negative partial u partial z equals also 0, and that's gravity. Now another example is, let's say I know u is a function of x, 1/2 kx squared. Then how do I calculate the force here? So the force is negative partial u partial x equals negative kx. Okay, so that's exactly the Hooke's law for spring force. All right, so I hope that makes sense, that we can go from force to potential energy definition, and we can also go from potential energy to force definition. That will be important for some special unknown forces. Maybe it's a way to discover new force. Okay, that's all. Thanks for watching.